Hello, calculus students. This video is going to walk through your official 6-1 Part 2 lesson, which is where we revisit the idea of an area between curves, but this time we are looking at things with respect to y. So in general, we can find area with respect to y by imagining our rectangles being stacked vertically, laying horizontally but being stacked vertically, as opposed to standing up and then being stacked horizontally. So let's imagine this curve for a minute. We're going to call this x equals f of y. So this would be some function of y that helps me evaluate these different horizontal distances. So I want us to think for a moment, when you have a point on a curve, right, an x and y ordered pair, the x coordinate would be how far you had to move to the right from the origin or left, and the y coordinate is how far you move up or down from the x-axis. So basically the x coordinate could be thought of as a function of y if I can get the equation in terms of y, and it will help me understand how to find these varying horizontal lengths. So for example, this horizontal distance right here, let's call this y1. That x value could be determined by plugging in whatever this y coordinate is here into my equation, whatever this equation was, that's been written in terms of y. And this is a nice short little x length, right? If I look at it down here, it would just be this length, right? That would be my x1 is my horizontal distance from the origin, and it would be based off of whatever this y value is when I plug it into the equation. Whereas if I choose a y value, say down here, I notice I get a different x length. This one could be determined by plugging in this different y coordinate into whatever this equation is, and it would spit out a different length, right? This length, this horizontal length would be considered my x2, so to speak. So I just wanted to kind of point that out, that these horizontal lengths can be understood as functions of y if my equation has been rewritten to be in terms of y. Then suppose you're wanting to find this area that is enclosed between this curve and the y-axis. So this area in yellow here. So I could essentially lay rectangles sideways like this. Just like when we used to stack them like vertically, I could lay them horizontally and just have all of these rectangles filling in this area. And I could just do a series of adding up base times heights again. So each of these little rectangles would have these different like change in y thicknesses, which would be understood as the base of each rectangle. And then the different f of y values, which are giving us our different x lengths, right? The horizontal lengths that go from the y-axis to the curve. Those are found by evaluating the function at these different y points. That would be considered the height of each rectangle. Of course, they're laying sideways. Maybe we could think of it as the length. We could also think of it that way, because you can think of the area of a rectangle as base times height or as length times width. So each of these little dy's would be like the thicknesses, the width of each rectangle, and each of these f of y values would be like the length. And then you would just multiply your length times width, or base times height. You add up infinitely many of them, but this time we are stacking them from bottom to top. So I would go to my lowest y point up to my highest y point. So I'd be summing all along up here. So I would integrate from a to b, but this time it's a y value of a to a y value of b. And this integral is how we would find the area of this region in yellow in terms of y. This integral would just spit out a number that would be telling me how many square units that area is. So that is the area with respect to y in general. Like if I just had one equation and I'm kind of looking at the area between that one graph and the y-axis. Now remember, the y-axis is where the x values are 0. So in a sense, it's like I'm subtracting 0 from the longer x values to get these lengths of these rectangles, or the heights of the rectangles. So now in 6.1, though, we're looking more than just at area between a curve and an axis. We're looking sometimes at area between curves. So sometimes maybe an image that looks like this. Here's my x-axis, my y-axis. Maybe I've got like a parabola going sideways like that, and then maybe a linear function angling downward, and maybe this is the area I want to find. So that area could be found with respect to x, but it turns out that the process in a situation like this is simpler if I instead look at this with respect to y. So like when we were finding area between two curves with respect to x, we would need to find points of intersection. So that would be that and that. This would be my lower y value, and then this would be my higher y value. So we'd be integrating from the bottom to the top. This curve could maybe be understood as one function of y, so x would be f of y. This line could be thought of as another function of y. We could get equations for both of these that are in terms of y. And then we could find basically the base and heights of rectangles laying horizontally. So kind of what we're always picturing is just filling in the area with infinitely many rectangles. And so each of these rectangles has a different height or length, however you want to call it. And it's because the difference between these two curves is different for different y values. So to find this length between this, you can think of this as x1 and this x2 over here. So these would be like two different x coordinates. To find the distance between them, I simply subtract. So each of these heights, if you will, or lengths, if you want to think of it that way, of these all these different rectangles, would basically be this x coordinate minus that x coordinate. But I would want to write that in terms of y, so this could be like the way I find my x coordinates for x2. This could be the way I find my x coordinates for x1. So this could be thought of as f of y minus g of y. The x value that was further right, the greater x value, and then minus the lesser x value. And that will give you the distance between the two. And it changes depending on what y is. If you have a lower y value, maybe it's shorter. A middle y value, they get longer, and then a taller y value up here, they would get shorter. And so you have all these different varying heights or lengths, if you will, of these horizontal rectangles where the bases are still dy. That's the thickness in between, right, which is a change in y. We could also think of that as the width of each rectangle. And then you just sum up the rectangles from A to B. Again, these are y values of A and B based on the points of intersection. I would do f of y minus g of y to get the heights of my rectangle. Multiply that by dy to get the thicknesses or the bases, the widths, however you want to think of it, of each rectangle. Sum up all the rectangles, and that gives you the area of the yellow. Okay, so again, I'm going to write down this is the height, multiplying that to the base. So these are areas of rectangles. This integral is summing up infinitely many of them, and it's giving me all this area. So we're going to keep that general process in mind with our following examples. Example 1 is similar to one of the practice tasks we had done at the whiteboard, where I was given functions that were in terms of x, and then maybe other lines, and asked to find the area bounded, the area of the region bounded by those graphs. So this example can be done in one of two ways. But first, it's really helpful to sketch the picture, sketch the graph, so I can see what the region is in the first place. So I notice that this is a square root function that has been shifted 2 units to the right, and then it's going to go up and to the right from there. This is a linear function that has a y-intercept of 8 and then a slope of -1. So it'll kind of go down this way. And so the region that I will be wanting to find the area of is this here, because this part is the y equals 0 line. Y equals 0 is a fancy name for the x-axis. So that's the y equals 0 boundary. This is the 8 minus x boundary. And then this is the square root of x minus 2 boundary. Okay. So if I do find this area with respect to x, I would have to evaluate this in parts. I'd have to do area number 1 and area number 2, because the area for region 1 is between the square root function and the x-axis only. It's not between the square root and the linear function. That would be like this part over here, which I'm not trying to find that area. Then in region 2, it's the area between the linear function and the x-axis, not between the two curves, because that would be up here, and I'm not trying to find that area. Okay, so I need to find a couple of things. One of the things I need to find would be this point of intersection right here between the two. So I'm going to set up my equation to find when they're equal to each other. So I squared both sides, FOILed this side, and then got everything over to the other side, got 0 on one side. Now I will factor, and I get intercepts of 11 and 6. So one thing that you have to keep in mind when you're solving these type of equations is sometimes you end up with what we call extraneous solutions. And in this case, that would be the x equals 11. The x equals 11 solution would be if I was allowed to let my square root be negative, and then they would meet somewhere over here. But since I'm not, I got to throw that solution out, and the one I'm looking at right now would be here. This must be where x is 6. The other thing I need to know is where the linear function hits the x-axis. That's this one here. So I would just want to set that equal to 0, and then I would end up with x equals 8. And then because this square root function had a transformation, it would move 2 units to the right, I know that it has an x-intercept of 2. So if I do find this area with respect to x, I would have to set it up with 2 integrals. I'd have to integrate from 2 to 6, and I'd be taking the antiderivative of the square root of x minus 2, and then I'd add that to this area, which I could just do the area of a triangle here, or I could integrate from 6 to 8, and it would be this equation of 8 minus x. So that is option number 1, is to evaluate this. Which here you'd have to do a u sub and yada yada, okay? This one you wouldn't. You could just take the antiderivative of each term, da 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 da. I won't go through this part now because that's a chapter 4 thing. But anyway, that's what you'd have to do to find this area with respect to x. Option number 2 would be to kind of change things to be in terms of y. I'm just going to draw the same picture. It has the same points of intersection. Here's where x is 6, here's where x is 8. And then I could find the y coordinate for that point by simply taking 6 and plugging it into either of the equations. So maybe I'll do the 8 minus x equation. So when x is 6 for that point, y is 2. So I could consider this to be something I could sum up from the y value of 0 to the y value of 2. And it would be this x value minus that x value. So I would just need to get this equation in terms of y. So I could subtract 8 from both sides, divide everything by -1, and I can think of these x coordinates that go all the way from here all the way to that line, I could think of them as negative y plus 8 values. Okay, so that's how I find x coordinates along the line, and then x coordinates along the parabola. So that equation was square root of x minus 2. So if I square both sides and then add 2, I know that the x coordinates along this curve, all these lines I'm drawing here, could be found by doing y squared plus 2. So now, if I subtract these x values minus these x values, that gives me the distance between them. So I could find all these different heights, and I could sum them up from the y value of 0 to the y value of 2. And I would do the negative y plus 8. Those are the greater x values because they're further to the right. And then minus the y squared plus 2 x values because those were more on the left, not as great. And I'd be evaluating this one integral. Would be the other way to find this same area here. So for that one, I would just take the antiderivative of all the pieces, distribute the negative here, and then evaluate them from 0 to 2. And I get 7 1/3 would be my area of that region, which you should end up getting the same value if you use this integral setup. Should also result in 7 1/3. And I'm fine, I'm completely fine no matter which option you choose to use for a question like this that could go both ways. The reason I started with something like this is just for you to see the advantage to sometimes switching things over to be in terms of y, because sometimes you will have no choice. So if you could turn over to the back part of your note guide, that's what these examples are on the back. Sometimes you are given functions in terms of y and you basically have no other choice really. I mean, you could try to get these in terms of x, because that's what this is. This is an x value, that's an x value. But it would be easier to just continue working with things in terms of y. So I am going to go ahead and attempt to sketch these. So here I have x equals negative y, which really, that one is not that hard to switch over. I can think of that as y equals negative x. So it's basically a linear function that just goes through the origin and has a slope of -1. This one, I would probably leave it factored. I would set x equal to 0 and then solve for y. And so these would be like the two y-intercepts of this graph. I notice also that if I distribute out the y, I end up with a negative y squared. So that tells me it's going to be a sideways parabola that's opening to the left and hits the y-axis at 0 and 2. So something like this, something like the picture I sketched earlier. So we've got the linear function with the negative slope, we have the sideways parabola facing left, and then we've got this region enclosed between the two of them that we're trying to find the area of. So I do need to find the points of intersection because I'm going to have to integrate from the bottom point of intersection to the top. Although it looks like this one would be at y equals 0 because both of the y values are 0 when x is 0. It's this one that I would need to find. So I would have to set these equations equal to each other and solve for y. And so when I do that, I get 0, the one I already knew about, and then I get 3. So this must be up at the y value of 3. So I know that if I integrate with respect to y, I'm going to be going from the lowest y value of 0 up to the highest y value of 3. So these again are y coordinates when I integrate with respect to y. And then I'm going to be looking for the lengths, if you will, or the heights, however you want to think of it, of these rectangles. so that I can sum up all their areas. So the heights are this x value minus this x value, the greater x value minus the lesser x value. So the x value along the parabola is defined as y times 2 minus y. The x value along the line is defined as negative y. So these are how you get those two different x values. And if you subtract the two of them, you get the distance between each curve, which would create the length of a horizontal rectangle. We could think of it as the height of a sideways rectangle. And then the dy is the thickness, the width of each rectangle. So I'm going to write it this way. Y times 2 minus y minus negative y. That is the height of my rectangle, times dy, that's the base. These rectangles are laying horizontally and they're being stacked from 0 to 3. So I would just need to evaluate this integral to get the area of that yellow section. So now I will just kind of slowly work through the process here. Distribute, combine like terms, and then take the antiderivative. Evaluate at 3, at 0, and then subtract. So it looks like the area of this yellow region in here, all of this stuff in here, is equal to 4.5 square units based on these base times height, height times base, area problems summed up from 0 to 3. Okay, so in example 3, I just took this one out of the textbook, like homework practice, because it's just an example of how things can get complicated, fairly quickly. I'm sure you have experience with that. This wants us to sketch the region bounded by these graphs and then to find the area of that region. And again, all these things are like in terms of y, so we're going to want to integrate with respect to y, so I don't have to try to get this in terms of x. But keep in mind, like f of y is just an x value, g of y is just an x value. And in fact, this one here is basically saying x equals 0, and then that's basically saying that's the y-axis. This is a very fancy way of saying the y-axis. Okay, so I'm going to start with that. The y-axis is one of our boundaries. Here's the x-axis just for some perspective, and then the y value of 3 is another one of our boundaries. Okay, so I know it's got to be between these and these. Let me do that again. So this line, and then this curve. So I'm going to just start plugging in some y values because I don't know what this curve looks like, but I could get a few points. Okay, so like for example, if y is 0, then I get 0 over 4, which is still 0. So I know that I have a point at 0, 0, which is a nice start. And maybe I'll just plug in 1 and 2 and then 3. So if I plug in 1, I get 1 over the square root of 15, which don't know exactly what that is, but it's small, right? This would be close to 1/4, not exactly. If this was the square root of 16, it would be 1/4. So it's almost there, but not quite. So let's see. This will be the x value of 1. So 1/4 would be like right there. If I plug in the y value of 2, I get 2 divided by the square root of 16 minus 4, which equals 2 divided by the square root of 12. Let's see, that would be 2 divided by 2 rad 3. So it's like 1 over rad 3, which is less than, or actually I guess it would be a little bit greater than 1/2, because that's almost 4, but not quite. So this would actually be greater in value, a little bit than 1/2. So we'll just say approximately 1/2. So like right here. And then when I plug in 3, which is my boundary anyways, I get 3 over the square root of 16 minus 9. So 3 over the square root of 7. Let's see, that would be approximately 3 over... it'd be a little bit more than 2, but not quite 3. So we'll say like Okay, I'm like totally cheating here. We'll say 3 over 2.5, which would be about 3 over 5/2, which would be about 6/5. So like a little bit bigger than 1. A little bit bigger than 1. So I don't know, somewhere like over here. And it looks something like that. So I haven't graphed this whole function, but I've already found the region, basically. It's going to be in here. And again, the equation to give me these x values is y divided by the square root of 16 minus y squared. So I plug in these different y's and it tells me the different x horizontal lengths, how far right I'm moving, basically. So, and I go from the y value of 0 up to the y value of 3. So I'm going to integrate from 0 to 3. And I basically am just taking these distances that go from the y-axis over to this curve. That's how I'm determining like the heights of each of these rectangles. So basically it would just be this equation that is determining the height of each rectangle. Then of course the dy is determining these little thicknesses to give me my bases. And then the integral is adding up infinitely many of these horizontally laying rectangles. So to evaluate this integral, I would need to use a u sub. U would have to be like the inside of the square root. Du would be negative 2y times dy. So du divided by negative 2 would equal y dy. So a little restructuring of this integral. And I have 1 over the square root of 16 minus y squared, and then I have times y dy. So now what I'm going to do is replace part by part from y to u. So this will get replaced with u. This will get replaced with du over negative 2. The 0 will get replaced with 16 minus 0, which is 16. And the 3 will get replaced with 16 minus 9, which is 7. Okay, so I am going to now integrate from 16 to 7 of 1 over rad u times du over negative 2. So that would become negative 1/2 integral 16 to 7 of u to the 1/2, u to the negative 1/2, because that was in the denominator, times du. And then because my limits are now out of order, I'm going to make them go to the correct order. I'm going to reverse their order, which would then multiply this by a negative 1 to be able to reverse the order. So really, I'm going to integrate 1/2 integral from 7 to 16 of u to the negative 1/2 du. So the antiderivative of that would be u to the 1/2 divided by 1/2, evaluated at 7 and then at 16. Those cancel out. So it would be the square root of 16 minus the square root of 7, or 4 minus the square root of 7. That value, unit squared, would be this area here. All of this area right in there is found to be 4 minus the square root of 7. Now this, of course, was all assuming we don't have a calculator, but just so we can kind of understand what that would be. 4 minus the square root of 7 is about 1.354 units squared. So not a lot of area. But that kind of makes sense considering the fact that these x coordinates were all fairly small. This was just barely bigger than 1. So these were like all really short heights. And then I only had to go from 0 to 3. So not a lot of area there. Okay, so that concludes the video portion of the lesson, but now of course there is the textbook practice that I hope you guys will work together on during class, because on Thursday when I'm back, we're going to be moving on to volume. I will be available Thursday lunch for questions, and so I'll see you then.